Okay, so today we will cover decision tree. You have cover regression. You also have cover neural network, um, in which neural network can perform regression at the same time also can perform classification. So today we will move on to another topic called decision tree. So this is one of the method used for classification. Okay. So what is the decision tree? Okay, so for if you look at the diagram on your screen, so this is one of the example, a basic example on the decision whether we want to accept the offer or not. So this is like to classify whether we want to accept the new offer. Okay, so if you look at the tree, it start with the root. Okay, so this is your main root. So root will consist of the value of the attribute. So over here we say if the salary is at least 50,000, then if yes, we go here. If the duration to reach the office is more than 1 hour, then we will decline. Otherwise, we will move on to here and then we say if they offer free coffee. If yes, then we accept the offer. Okay. So one thing that we need to do to know about decision tree, we have the root node, which is where you start the checking the values, and at the end of your you will have the leaf. So the leaf will be the trust level, so whether you accept or not accept. Okay. So the issue that we want to look at here is how do we construct the tree? How do we choose the attribute to be used to split your tree or split your data? Okay, so we will look into entropy and also in information gain on how we can use this method to construct your tree. So for example, um, if we have two variables that can be used to represent your data, so we have two classes here. So you know that we have two classes because we have the red and also the blue. So based on the distribution of the membership of your data, so we can construct the tree saying that if x1, which is this one, greater than w10, okay, and if w2 is greater than w20, okay, if x2 is greater than w20, then we say that they are belong to class number 2. Otherwise, they belong to class number 1. Okay, so that's how we look at the data that we have here. Then we can convert them into decision tree. But during the modeling, they will choose the best attribute and the attribute value that we can split the data in order to have majority of them belong to class 1. Okay, so in each of the leaf, our get or our aim is when we split the data into 2 or 3, at the end of the tree, the leaf of the tree, we want to maximize the purity of the membership of the class, so belong to one class only. Okay, so when we talk about the value that we have here, this is univariate, uses a single attribute xi. Okay, so we can split them into 2 um, by comparing the value of the attribute with a certain value here. So you can split them if xi is greater than this m. If this is yes going here, no going here. Or this is binary split. Binary split meaning that we have two ways only. But if we have n ways, so basically we can split the data into more than two. So maybe we say this is xi is greater than a certain value, contohnya W1, and then over here is between xi is greater, so the one should be less or equal to Wi, and xi is greater than W2. That is not in this path. And then for this one, so it should be xi less than or equal to W2 and xi is greater than W3. So you have a partition which you want to go depending on the value of your x. Could also use multivariate. So multivariate is when you have this condition. You have two conditions. Okay, so if this value fulfill your requirement, and this also, so you will go to middle one. So that is multivariate. Uses all attribute x. So this is the internal decision node, which is here. Okay, and at the end of your tree, you will have the leaf. Okay, the leaf. They show the class label. And if you remember the logistic regression, they use numbers to represent the value that you going to the bottom one. So that is the regression problem that we have. So the learning is greedy, meaning that we will find the best splitting, that best group the data into one label only. So that means the purity of your data partition is very high. So one partition may have a single label in that partition. So that is the aim. So what happened is that during the build up of the decision tree, we will split the data recursively, which means that after we split the data into two partitions, we will continue again splitting the two sub data. So for example, if this is your data, you split them into two. Okay, so we recursively split the data again into two again until we reach where all the member of this partition belong to only one class. So that is considered as your stopping condition. So this is what we call divide and conquer. We divide the data into a partition. In each partition, they have same label. Okay? So we only stop splitting when you have all the labels in that particular partition belong to only one label only. Or we may stop when we have reached the predefined depth of 3. So in this case, we have two level depth. So let's suppose we say, okay, we will stop at the level number 4 or depth number 4. So we'll only split the data up to level 4. So this also considered the stopping point. So when we talk about the entropy or the purity of that particular group, so for example, if we have one group here and then plus, minus, so that means all the member in this group, they belong to positive and two belong to negative. So that is where we have your um, where your positive, you only have half of them. So half of, because this one we have 4, right? So the positive one we have 2 over 4. Okay? So when your positive sample is half only, so you will reach the maximum value of entropy. If all the member of this particular group belong to positive, which means 4 over 4, you are here, and we say that your entropy will be 0. So the way we get this value is that we can use this formula. So one part of the formula will deal with the positive labels, and the other one will deal with the negative label. So this one will measure the entropy. The entropy show you the value of the purity of the partition. If the value is 0, means 0 here, that means all of your number here belong to one symbol only, which is the positive. If your entropy is 1, that means 50% of your sample in this partition belong to another label. Okay, so we will show you how do we compute this entropy later on. So for example, we are looking at this group. So we have the symbol A, we have 5 over 10. Okay, and symbol B, we have 3 over 8. So if you want to compute the entropy or the purity of this particular partition, so the first thing that we need to do is we have to use this formula. This one. So first we look at the positive and then the negative. So if you look at here, so let's assume the A is positive and the B is negative. Okay, so when we form the formula here, so this is for the positive, this is for the negative. So this is the probability of having symbol A. So we have the 5 over 8 over 8, and then plus the probability of having symbol B. So once we compute that one, we get 0.95. So this is the entropy for this one. Okay, so based on our explanation just now, if your entropy is 0, that means all the member that particular partition belong to one symbol only. But in this case, we have 5 belong to A and 3 belong to B. So basically, we have 50-50. So that's why your entropy here is going 1, going towards value 1. Okay. Okay, this is another example. Okay, so this is the data that we have for deciding whether we want to play or not. So it depends on the outlook, depends on the temperature, depends on the humidity, and depends on the wind. Okay, so let's suppose we take the outlook to be the attribute that we want to split our data. So in order to split the data, we take the value, all the unique value that we have, sunny, overcast, and rain. So we only have 3, sunny, overcast, and rain. Okay, and for each of these row, we collect the first label here and put it here. And for the sunny, we have 3 no's and 2 yeses. So for the sunny, we have 1, 2, 3, 4, 5. So we are looking at this one. So that one and this one. So 3 no and 2 yeses. So if you look at the outcast again, so the outcast will give you 4 yeses. The rain will give you 3 yeses and 2 nos. So for each of these grouping, we can use the entropy to measure how pure is the partition with respect to the class label. So we can compute this one, 2, 3. So for example, we're looking at the sunny. So the probability of having sunny, which is yes and no. So we have 2 over 5 and 3 over 5. Okay, for the no, we have 3 over 5. Okay, and then for the yes, we have 2 over 5. And we get this particular value. So this is the entropy for this particular partition based on the variable outlook, the value sunny. And if you look at this one, so we only have 4 yeses. So that means we have 4 over 4 log 2, 4 over 4. At the end, we get 0. So the entropy is 0, meaning that the membership of this particular partition is belong to one class only. So very pure. So over here we can say that when your entropy value is 0 or nearer to 0 or going to 0, you have high purity. If you have your entropy to be nearer to 1, that means 50% of your classes different belong to another class, so 50-50%. So if you look at this one also, this is similar to first partition because over here we have 3 yeses and 2 no. So similar calculation, similar value of entropy. Okay. So di sini we show you we can pick the variable outlook, then we can take the values to split your data, and we look at whether particular column is a very good column that we can use to split the data. We could use temperature, we could use humidity, and we could use wind also. Okay, so okay, since we have three partition here, we have the value for this one is 0.96, and this is also 0.96, and this is 0. So to capture the total entropy, we cannot simply 0.96 plus 0 plus 0.96. So there must be pemberat di sini, a weightage. So the weightage we take is, okay, how many member we have here divided by the total number of number of row that we have here. So basically over here we say 5 over 14 because we have 14 row. And then for the 0 here, we have 4 over 14. And then lastly over here, the weightage is 5 over 14 because we have 14 rows here. So this will encapsulate all the total entropy that we have. Let me show you the example here. So basically this is the individual partition, and this is the weightage that we have. So this one belong to the number of this one refer to the number of member belong to that particular group, and this is the total number of item that we have in our record. Okay, to show you the full calculation, okay, before that we have to look at the finding the best split. So Like I mentioned just now, we can split the data using the outlook or the temperature or humidity or the wind. Okay, and to find the best splitting is when you have high information gain. So how do you compute the information gain? We take the entropy before the splitting minus the entropy after the splitting. So example like this, if we have split them into two partitions, so this is not pure because we have some of the green membership on this side and also this one also. This is what we call very pure because they are divided into two partitions and each partition maximize the entropy that they have. Okay, minimize, which is zero. So we say that this one is high purity and this one is not very high. So, or we can say impurity. So this is high impurity. This is low impurity. So this one is minimum impurity. This one is maximum because we have a mixture of the green and the plus. Okay. Now we go back to this info gain. So in info gain normally used to decide which attribute is best used to split your data. So for each of the feature that we have, we compute before the splitting using this particular feature and after the splitting using this particular features. So if and also for each of this entropy. So after the splitting, we have a few partition. So this one referring to partition 1 up to n, and this is the weightage of that particular partition. And this is the formula that we have just now. So this is for each of the partition, and this is the weightage. Okay, okay, how we can use this formula? Okay, let's go back to this example. Okay, so from the calculation, we know that this is 0.96, right? And this is 0.96, and this is 0. Okay, so to calculate the total entropy after you splitting, because this way you split the data into three based on this variable or attribute and based on the value that we have here. So we split the data using this attribute, and after the splitting, we get this. So the total entropy after the splitting will be take 96. So this is the weightage because we have 5 of them. 1, 2, 3, 4, 5 over 14. So we have 14 here. Then this is 4 over 14. This is 5 over 15. And this is the total entropy after. Before the splitting will be called. So before the splitting, okay, so let me write this one. This is after you splitting. Okay, before you splitting, basically we are looking at this one. That is initial. So before the splitting, we have this formula for because we have 1, 2, 3, 4, 5. Okay, 5. Okay, before the splitting, we have 5 over 14 log 2, 5 over 14 plus 9 over 14. So the 9 is for the yes. Log 2, 9 over 14. So when you compute this one, you get is 0.94. So this is before you splitting. Okay, before you splitting, you still have a whole bunch of data. So it means we have one partition for all of this. So after you split them using the Outlook, then the value is 0.68. So to compute the info gain, we subtract the entropy after split from the entropy before. So your before is 0.94 minus 0.68. So your IG is 0.26. So meaning that before you split the data, if they're still in one table, then you use the variable outlook and use the value to split them into three partitions according to the number of unique values in that particular variable, and then we compute the entropy. Okay, so the aim is we want to find the attribute or the variable that has the highest value of IG. Means the information gain that you get when you split the data. So we want to maximize that one. Okay, so we could test for temperature, we could test for humidity and wind and so on. Okay, so let me give you one more example. Okay, one more example. For example, we have this data set and we have two variables. Feature 1 for the count and feature 2. Okay, so before we split the data, we have this one table. So the entropy will be 5 yes and 5 no. So this is before splitting. Okay? So this is before you splitting. Okay, after you splitting using the count here, so given the feature 1 count here, okay, so in count we have 4 unique values, A, then B, and then C, and then D. So for the A, we have 2 no. Okay, so 2 over 2 log 2, 2 over 2, and this is the weightage because we have 10 rows, and then in this partition we only have 2, so that's why we have 2 over 10. And then the next one is we have 2 no's and 1 yes. So this is for the no's, and this is for the yes. And the weightage will be 3 over 10, because in this partition we only have 3 over number of row that we have. And then this one also we have 3 divided by 3, 3 divided by 3, and this is 3 over 10. And then lastly, this one we have 1 over 2, log 2, 1 over 2, because we have 1 yes. So this is for the yes, and this is for the no. And the weightage is 2 over 10. So we can solve this one. So in order to compute the information gain, so we need to subtract the entropy after you splitting from the entropy before you splitting. So this is the formula that you have. So we can repeat the same thing for the total one. So the total one here. So whichever give you the higher information gain, then we can use that one to split your data using that particular attribute and all the value that we have in that particular attribute. So that's how the tree was constructed when we perform the training. So given the data that we have, we will look at the features and then we will pick the variable or the attribute that best used to split your data to maximize the information gain. Okay. Okay. Let's take a look at one of the application of decision tree in which we are looking at the loan application. Okay, so we have 5 steps here. First one is to collect the data. So the data that we have represent the loan application from a credit agency in Germany. Okay, and these are the sample data, the structure of the data that we have. So basically, we are looking at reading the file from the credit Excel. Then we say that the string as factor, meaning that all the character will be maintained as factor or labels. And this one will show you the structure of the data that we read from here. Okay, now we check some of the value that we have. So for example, we're looking at the checking balance or the saving balance. So at the top here, it shows you the attribute value for the checking balance. And the number down here tells you how many records belong to that particular values. So we can use the table to look at the number of rows that are consisting that particular value of that particular attribute. We could also perform the summary for the month loan duration. So the month loan duration maximum is 72. Okay, we could also perform the summary for the amount. So we can see minimum loan, maximum loan, and mean and median. And we can look also at the distribution of the dependent variable here. So what we want to do here is that we have a total of 30% of loan went into default. Likely to default means they are not paying they are not paying their loan. Okay, so based on this, we want to construct a tree that tell us some of the condition that we can apply to filter or to decide whether a new application can be rejected or can be approved based on the decision by the decision tree. Okay, before we proceed, we have to do sampling because we want to split the data into 90% for the training and 10% for the testing. Okay, so what do? We use the sampling method, and then because we have how many data just now? We have 1,000 objects here. So we want to get 900 of them, but randomly. Okay, so I will pick 900 values from this 1,000. So I will store in the trend sample here. So if I type the value of the trend sample, basically this is the index of the row that I will take as a training sample. So over here, I will divide 90% belong to the credit trend and 10% belong to the credit test. Okay, and if I look at the proportion of the training data, I still have 70 to 30%. So that means our sampling method is correctly conducted because we get the same proportion for no and yes. We maintain the percentage here. Okay, and we also look at the testing data set. So we also maintain 70 to 30%. So once we split the data into a training and testing data set, then we can install the package C50. So this is one of the decision tree. They call it last time they call it C4.5, but now they have upgraded the decision tree to become C5.0. Okay, and then we load into the memory. So how do we call the decision tree or modeling? So we just type C5.0. We provide the training data set and also the class of that particular training set. and we are building only one tree. Okay, so once we perform the training, we get the model here. Okay, we take the model here, and then we will perform the prediction for the test data set that we have, and then the type will be class. So the P here will consist all the label for your test data set here. Then we can compare this value of P with the actual label of your test data. Okay, so now here we're calling the C 5.0, and then um, meaning that I will get all the training data set except the last column, which is the default, which is the dependent variable. Okay, I include all except last column. And then the last column will pass us the label because you want to use this one to um, be model using the C 5.0. So over here, I will pass my data, and over here, I will pass my labels. Okay, so once we have finished with the training, then we can look into some of the condition that we have here. So if we type summary and credit model, okay, this is the model that we have trained. Okay, so according to the decision tree, what you can see that if the checking balance is greater than 200 Dutch money or unknown, so that means you are not likely to default, meaning that you will pay the loan or you will service the loan. Okay, but if your checking balance is less than 0 and in between 1 and 200, and also your credit history is perfect and very good, so you are likely to default. Okay, so in the bracket here, it tells you how many correctly classified and incorrectly classified sample that we have. So based on this result, this is what we can say. Okay, if the checking account is unknown or greater than 200 Dutch money, then we classify as not likely to default. Okay, so not likely to default, meaning that you will service your loan. Otherwise, if the checking account balance is less than 0 Dutch money or between 1 and 200 Dutch money, and the credit history is perfect or very good, then we classify as likely to default, meaning that you are likely to not to pay the loan. So this is found based on history data. So, that is some of the knowledge or some of the tips that we can get from this decision tree. Okay, so how do we evaluate? How do we evaluate the performance of this? So basically, we are looking at the prediction here. So we get the credit model here, the model that we train, then we pass them with the test data set. And then since we perform the prediction, so this will consist all the labels for the default, which is likely to default or no. So when we the value predicted here against the actual no, this is the actual credit default. This is the predicted one. So basically, we are trying to compare between the actual and also no. So that means we have 59 predicted as no, and the actual value is also no. So this is okay. Okay, so this is true positive, and then this is true negative. Two are okay. But we have this 19 and 8 because we predict them to be no, tapi dia punya actual label is yes. So this is misclassified. And And this one also, we predict them to be yes. The actual the data show that they are no. Yeah. So the error would be 27 divided by 100 because we have 100 samples. Okay, so this is the error. And the accuracy will be 73% because you 100 minus 27. Okay, since this one they only show you one tree, basically we can build more than one tree. Okay, so how do we improve them? So we can build them or get more than one tree. Okay, so for example like this, we repeat the same thing here, but we trial 10 here, meaning that we will have 10 trials in order to get another tree, which has better performance. Okay, so we simply need to add additional trial parameter indicating the number of separate decision tree to use in the booster team. So which means we have 3 here, and then we pass again another 3 here and 3 here. So all together here will become random forest because a collection of decision tree. So this number tell you how many trees that you will be training, then keep improving. So if we compare the performance of having 10 trees, so now we only have 18% as your error. This is your error. And your accuracy will be 82%. Okay, so this is okay, this is okay, and this is the one that is misclassified. So you can test with another value here. So it could be 25, it could be 18, and there is no rule saying that you can only try 10, but we could also use different values for that one. So in summary, when we talk about the decision tree, we are looking at the entropy and also the information gain to split the data. So based on the value of the entropy or the information gain, we will find the best splitting that can maximize the accuracy of the performance. So any question?